This is the problem we will be solving. This problem states, in the Olympics big air snowboarding event, the large ramp launches athletes into the air at a 50-degree angle. One athlete must do his trick when he reaches the highest point of his jump. If he has an initial velocity of 20 meters per second, after how much time and at what height should he do his trick? If the trick lasts 0.27 seconds, how high off the ground is he when he finishes the trick? As you can see, we already have a diagram drawn and filled in with all the information we know from the word problem. The solid line represents the path that the snowboarder takes down the ramp and into the air. The dotted lines form a right triangle that will be helpful in solving for the answers of the questions. Under the diagram, I redrew the triangle and first filled in the 20 meters per second, which we know is the initial velocity of the athlete, and the 50 degrees, which we know is the angle that the athlete comes off the ramp at. Using SOHCAHTOA, we can solve for the horizontal and the vertical initial velocities. Now, it's important to know that you'll be solving for the velocity of the horizontal and vertical component rather than the horizontal displacement and the vertical displacement. Since we will be using the 20 meters per second, which is a velocity, that means that our other answers will also be velocities. So in order to solve for a horizontal velocity, I used cosine. So cosine of theta is equal to adjacent over hypotenuse. After filling in all the information we know, we get cosine of 50 is equal to x over 20 meters per second. Multiplying both sides by 20 meters per second to isolate the x, and then plugging it into a calculator, you'll get x is equal to 12.86 meters per second. Now that is going to be our horizontal initial velocity. In order to solve for the vertical initial velocity, we'll be using sine. So sine of theta is equal to opposite over hypotenuse. So again, filling in the information that we know, we get sine of 50 is equal to x over 20 meters per second. Multiply both sides by the 20 meters per second to isolate the variable, plug it into a calculator, and you'll get 15.32 meters per second. This is going to be our vertical initial velocity. So the first step to solving a problem like this is to set up a chart and to fill in the values that you already know. This is to help see what values you don't know and what values you need. So the chart that I made has our horizontal initial velocity, acceleration, final velocity, time, and displacement. I also have the same initial velocity, acceleration, final velocity, time, and displacement, but for our vertical component of our problem. So I've already filled in all the information that we know. So from our SOHCAHTOA with our triangle, we already know that the initial horizontal velocity is 12.86 meters per second, and the initial vertical velocity is 15.32 meters per second. For the horizontal acceleration, I have 0 meters per second squared. This is because there is no force acting on the horizontal that will cause an acceleration. And since there is no acceleration, that means that the final velocity will be the same as the initial velocity. This is not the case, though, for vertical acceleration. The force acting on our vertical is gravity, which has an acceleration of negative 9.8 meters per second squared. And the reason it's negative is because acceleration is a vector, meaning that it has direction, and gravity is a force that pushes down, making our acceleration negative. So this causes our final velocity to be the same speed as the initial velocity. See how they're the same numbers, but our final velocity is negative because it's going in a downward direction. So the only values that we don't have in our chart is our time and our displacement. And as of right now, the only information that would be helpful for us to solve the problem is to find our time. And in order to find our time, we must use the vertical values, because if we were to use the horizontal values with the equation that we're given, we would only end up with 0. So now that we have the time of the entire jump, we have to solve for the time where the athlete is at the highest point and the height at which he is at his highest point in order to determine when he should do his trick. Now I want to bring your attention back over to the diagram where I have filled in that at the peak of his jump, his velocity is 0 meters per second. This is his vertical velocity, and the reason that it is at 0 meters per second is because the negative acceleration has finally stopped the direction of the vertical velocity from going up, and the vertical velocity now begins to accelerate downwards. So at this top point is where the velocity changes direction, hence why it is 0. Now the equation we're going to use for this one is the displacement equation, which again is displacement is equal to vertical initial velocity times time plus half the acceleration times time squared. Now the nice thing about having this 0 vertical initial velocity is that this whole first part of the equation will be 0 times the time, and anything, as we know, times 0 is equal to 0. So we can just cross this part of the equation out and only worry about the half times the acceleration times time squared. So using that, we are going to start with the displacement is equal to 1 over 2 times our acceleration, which is negative 9.8 squared, or negative 9.8 meters per second squared. And we are going to be multiplying that by our time. Now for our time, I'm going to be using 1.565 seconds. And again, since it's time squared, we are going to multiply again by 1.565 seconds. Now the reason we're using 1.565 seconds instead of the 3.13 seconds that we've solved for before is because since we are beginning our equation from using values from the top of the jump, that only means that we're covering this half of the jump, which would be only half of the time because it is only the amount of time it takes to go from the absolute top right back to the bottom. If we were solving for the vertical displacement of the entire jump, then we would be using the 3.13 seconds. But that is not what the question asked, so it's not what we're going to be solving for. So again, with our unit analysis, we can see that seconds and seconds cancels out with the seconds squared, leaving us just with meters as our unit. So after plugging this whole thing into the calculator, you'll get negative 12 meters. Now, the reason that it is negative 12 meters is because, like I said, we're solving from the top of the jump to the bottom. And with displacement, again, being a vector, this means that it has direction. So the direction of this vector, since it's from the top to the bottom, is going to be negative because it's going down. But since we want to know the height, that the direction really doesn't matter, just because it's 12 meters going down, just as it is 12 meters going up. So our answer is going to be at 12 meters, he is at 1.565 seconds. So this answers the first part of our question, which is after how much time and at what height should he do his trick. He should do his trick after 1.565 seconds when he is at 12 meters in the air. Now that we have solved the first two parts of our question, we have to solve for the third part of our question. If you recall, the third part of our question states that if the trick lasts 0.27 seconds, how high off the ground is he when he finishes the trick? Now, to start to solve this, we are again going to be using the displacement formula, which is, again, displacement is equal to initial velocity times time plus half acceleration times time squared. Again, we are going to be using the 0 meters per second starting from the top. So again, this first part of the equation is going to cancel out since 0 times any number is going to be 0. So that will leave us with displacement is equal to 1/2 the acceleration, which is, again, negative 9.8 meters per second squared. So just like the last part of the question, we are not going to be using the full time of the jump. Instead, we are only going to be using the 0.27 seconds that the problem gives to us. So that means that this will be 1/2 times negative 9.8 meters per second times 0.27 seconds, and again times 0.27 seconds because it's time squared. The seconds will cancel out with the second squared, leaving us with just meters. And after plugging this into the calculator, you get negative 0.3571 meters. As you can tell, that is a very small number and definitely not the height off the ground that the snowboarder is when he has to finish his trick. Instead, this is actually the height, or more the distance from the top of the jump to 0.27 seconds away. So this will be this height from here to here, 0.27 seconds away. Again, it's negative because the direction is downwards rather than upward. So in order to answer our final question, we are going to take the 12 meters, which we solved for prior, which we know is how high the snowboarder is in the air when he has to start his trick. And we are going to subtract the 0.3571 meters because we know that he falls 0.35721 meters from his max height during the 0.27 that it takes for him, the 0.27 seconds that it takes for him to complete his trick. So this subtraction leaves us with 11.64 meters. Now 11.64 meters is how high off the ground that our snowboarder is once he finishes his trick. That makes this the answer to the final part of our question.